in our last video, we introduced the concept of a basis for a vector space. In this video, what we're going to do is we're going to look at, suppose I have a collection of vectors that's looking like it's going to be good for a basis for a space, but it's not complete. How can it doesn't like hit everything in my vector space. So how can I expand the set that I do have to make sure that I include everything? So we're going to start out with two theorems over there, and then we'll do an example over here. So theorem 16 states that if I have V equal to the span of n vectors, if this is a vector space, then some subset of it is going to be a basis. In other words, if you know that you can write your vector space in terms of a span of some vectors, then some subset of those vectors that span the whole space will be a basis. The only reason it wouldn't be that set itself is if that set is not linearly independent. If you have some duplicates or some redundancies, then it's not going to be a basis. So that's what theorem 16 is stating. And what theorem 17 states is if you have a finite dimensional vector space and you have a linearly independent set of vectors, then you can expand that collection so that you can find a basis. So what that means is you don't have to like start from square one. If you have some linearly independent vectors, it just doesn't span the whole space, you can find some and toss them in, and then that'll be good. So that's what we're going to do for example 23. We've got a space S, which is a subset of P2, and it's got two vectors in it. It's got x squared plus x and 1 minus x squared. And we want to extend this set to be a basis of P2. So two things going on right now. My computer fan just turned on, so I apologize if you can hear that if you're wearing headphones, but it's just going to make some noise now. Two things. Thing number one, we know that S is linearly independent because this first vector has an X term and this one does not. So there's no way that I can take this vector and create this one. Similarly, this one has a constant term, but this one does not. So there's no way I could take this one by itself and create this one. So these are two kind of somehow unique vectors. So that's the first thing I know. The second thing I know about this is that it is not all of P2. I know it's not all of P2 because in the last video, we saw that the dimension of P2 was 3. And that would mean we need 3 basis elements. So here we have just 2. So we're going to have to find one more to toss in. So one more linearly independent vector that's going to complete what's happening here. So with that in mind, let's find what's missing. Now, to start out with, let's write what a linear combination of these two vectors is going to look like. That's going to help us figure out what we're missing. So first, I'm going to write that as alpha x squared plus x plus beta 1 minus x squared. Now, as we've seen in P2, it will behoove us to write this so that the x squared term is, something x squared plus something x plus something. So let's do that here. I've got alpha x squared, and then I'm going to have minus a beta x squared. So that will give me alpha minus beta x squared. From here, I get alpha x. And from here, I'm going to get plus beta. So we know that an element in the span of S is going to have this shape to it. So now we have to see what's missing. One of the easiest ways to see what's missing is to take a standard basis and see which elements from that standard basis is this not going to hit. So for example, P2 has a standard basis of x squared, x, and 1. So we also saw that, excuse me, in our previous video as well. So let's see if we can write x squared in this form. So what that's going to mean is I'm going to have x squared is equal to alpha minus beta x squared plus alpha x plus beta. Now, because there's a 1 in front of the x squared, I know that 1 has to equal alpha minus beta. Because there's no x term, that means that 0 has to equal alpha. And because there's no constant term over here, 0 has to equal beta. You see a problem with this? So if alpha is 0 and beta is 0, there's no way I can take 0 minus 0 and get 1. So we end up with an inconsistent system. This is actually good news. It's not really sad news, because that means this is the missing vector that we need to complete our basis. So to expand or extend our basis, we're just going to toss in x squared. So I'm going to have x squared plus x, 1 minus x squared. And now we're going to expand it by adding in just x squared. Now, if I want to make sure that I'm hitting everything, let's also check these other two elements of the standard basis. Make sure that this new expanded version is going to hit them. So that just means we're going to have to find an eraser. And we're going to basically repeat this with that new vector included. So I've got alpha, this first one, beta, the second, and now we'll do delta x squared. So when I write this all out in the form that we're accustomed to now, we're going to have alpha minus beta plus delta x squared plus alpha x plus beta. So if I want to see if x is in this set, x is going to equal alpha minus beta plus delta x squared plus alpha x plus beta. And following our coefficients, we're going to get that this beast has to be 0 because there's no x squareds over there. Alpha is going to have to equal 1. And beta is going to have to equal 0 because there's no constant term here. Now this time, because we have this delta handy, we know that alpha is 1 and beta is 0. So I get alpha is 1. So we have 1 minus 0 plus delta has to be 0, which means that delta has to be -1. So now we have a nice consistent system. So this is telling us that we can write x in terms of these three vectors, which is what we need in order to be a basis. Similarly, we can do the same thing with 1. So let's check 1. That's going to equal alpha minus beta plus delta x squared plus alpha x plus beta, because that's sort of our properly formatted linear combination now. So here's my constant term, which means this has to be 0 and this has to be 0, and that one's got to be 1. So we have alpha minus beta plus delta has to equal 0, alpha has to equal 0, and beta has to equal 1. Again, we can take these two pieces, plug them up in here. So that's going to give me 0 minus 1 plus delta is 0, which means that delta has to equal 1. So again, we get a consistent system. So that means that we can express 1 in terms of these three vectors here. So yeah, so that means now we've been able to expand or extend, I don't know why I keep saying expand, but we were able to extend this collection of two linearly independent vectors to cover all of P2. Now, this doesn't mean this is the only possible one that could work. In fact, if we had started by looking at 1 instead of x squared, we might have decided to throw in 1 instead of x squared and see where that would take us. So there are a lot of different ways that you can approach these and multiple correct answers. So just make sure that you can justify your work, with a group member if you're comparing solutions or, things like that. Okay, so here's how we can extend our smaller set of vectors into our full vector space. Now let's look at some subspaces. Now, if you're in my class in the spring of 2021, I had a typo in my notes, so I'm going to fix that with the theorem that I write on the board here. So theorem 18 had a typo in my notes this semester, so make sure you make a note of that and fix it if you're using your printed out notes. So let me write that on the board and then we'll go through it. And just like that, the theorems are on the board. So let's look at theorem 18. In my notes in spring of 2021, what I did was the old copy paste mistake where I copied for the formatting and then forgot to change the text of the theorem. So theorem 18 should say, let V be a vector space with finite dimension n, and let W be a non-zero subspace of V. Then you can find a basis for W. In other words, if you have a subspace of a vector space, you can find a basis for it. It's possible to do so. And what theorem 19 says is that if you have a non-zero subspace of your vector space and you have a basis for that subspace, then you can extend that to a basis of the whole space. So if you can find a basis for a subspace, then you can extend it to the whole space. So that's what these two theorems are stating. If you're copying them down, you can pause here because I'm about to erase them so we can do the example that's written on the board behind me. Okay, we're going to erase. So while I'm erasing, let's talk about example 24. So example 24 says, let's let W be the span of three vectors. And these vectors are vectors from M to 2. So they're 2 by 2 matrices. And they're written here, VW and X. And we're going to find a basis for this space. And then we have to say, is that also a basis for M22? And if not, then let's extend it to a basis of M22. So there's quite a bit going on in this example. We're going to spend a bit of time here. But let's start out with this first part, finding a basis for W. And let's talk about why we can't just say, well, it's going to be VW and X. Easy peasy done, right? So we can't just state that because we don't know yet if these three vectors are linearly independent. We have the span piece down, so that's okay. We know that it's spanning the space, but we don't know that these three vectors are linearly independent. Maybe we have like a extraneous vector here. So how do we decide whether things are linearly independent or not? Well, we can see if we can write one vector in terms of the other two, or we can set a linear combination of them equal to 0. So it's up to you which of the ways you want to set this up. I'm going to stick with the traditional definition, which is a linear combination of them equaling 0. And we're going to see if it has a non-trivial solution or not. So I'm going to start out with AV plus BW plus CX equals 0. And we have to see, what we can get. So we're going to get, I'm just going to multiply all at once here. So everything in here gets multiplied by A. So we get 3A, 0, 0, 3A. Plus everything in here gets multiplied by B, because that's W. So we're going to get 0 minus B, 0. And then everything here is going to get multiplied by C. So we get 2C, 3C, 3C, 2C equals 0. Now, in this case, the 0 vector is the 2 by 2 0 matrix. So we get 0, 0, 0, 0. I always find it helpful to write my 0 vector in the form that it should appear instead of just writing 0 there so that I know exactly what I'm looking at, right? So if I add all of these up, I'm just going to add their components. So I get 3A plus 2C. Nothing, minus B plus 3C. Minus B plus 3C. 3A plus 2C. And this is going to have to equal our 0 matrix. Okay, now if I have two matrices that are equal, that means each of their coordinates have to be the same. And this is how we're getting our system of linear equations. So we're going to get 3A plus 2C has to equal 0 from the top left. From the top right, we get that negative B plus 3C has to equal 0. From the bottom left, we get negative B plus 3C has to equal 0. And from the bottom right, we get 3A plus 2C has to be 0. Now, if you, like I, are looking at that system here and say, got some redundancies here, right? This equation happens twice, as does this one. So if we're going to solve this system, we don't actually have to solve the two equations twice. Once is enough. So I'm just going to get rid of the duplicates here. That'll make our lives a little bit easier, right? So our goal here now is to solve this homogeneous system of linear equations. So how do we solve a system of linear equations? Well, we put together a matrix, we row reduce it, and we see what we get. So we're going to get 3, 0, 0, negative 1, 2, 3. And because this is homogeneous, you can opt to include a column of zeros or not. For purposes of this example, I'm going to throw them in just so we don't get confused. And then we're going to row reduce that using Gauss-Jordan elimination. And when I did that earlier, here's what I got. I got my first column is 1, 0. And I got 0, 1, 2/3, negative 3, 0, 0. So what this means in context of our problem is that we're going to end up with a parameter because we have a pivot position for A, we have a pivot position for B, but we don't have a pivot position for C. So this means we're going to have A equals negative 2/3 C, and B is equal to 3C, and C is C. Okay. Or more standardly, we've been using S's and T's for our parameters. So these would just be T's. And I'll remind you, I was able to jump here right away because I knew that this was going to be A plus 2/3 T. So I subtracted the 2/3 T from both sides to get this equation here, and then did a similar thing for the second equation. So we have a parametric solution, which means that we have non-trivial solutions to this homogeneous system, which means these three vectors are not linearly independent. Because they are not linearly independent, they are not a basis. They contain redundancies. So when this happens, so that we don't have to do like a whole bunch of more work figuring out, what's what I like to do is pick a value for T that's going to give me 1 for one of these things. That's going to make my life easiest. So if I pick T to be 1, then that means that C is going to equal 1, and that's going to make my life easy. Here's why it makes my life easy. So we know that if I have, from this equation, if I have AV plus BW plus CX equaling 0, that these coefficients is going to create a solution for us. So if I let T be 1, then here I'm going to get 3. And here I'm going to get negative 2/3. So what that means is I'm going to get negative 2/3 V plus 3W plus X is 0. And I can move those to the other side, get that X is 2/3 V minus 3W. So this way we're able to write one of the vectors in terms of the other two. Now I'll point out, like I said, I just picked T to be 1 so that I would have an easy way to get one of these variables equal to 1. I could have picked T, for instance, to have been negative 3/2. If I chose that, then that would have given me a value of 1 for A. So then I would have written A in terms of the other two vectors. Or if I had picked T to be 1/3, that would have given me 1 for B. So I could have solved B in terms of the other vectors. Okay, it's really just up to you, but this is where we have like lots of choice going on, right? Like there are lots of different bases that you can find. What this means though, since we're able to write X in terms of the other two, it means that we don't need X. So for our basis, we can get rid of X. Oh, bless you, kitty. And that means we can just use these two vectors as our basis. Okay, so I just had to check on my cat real quick, make sure he was okay. Yes, he's fine. But before I erase the board, I did want to make one comment or observation on this process. So we found that these two vectors are going to form our basis. And if I look at my row reduced matrix over here, we had a pivot in column 1 and a pivot in column 2. So those are corresponding to our elements V and W, our first two elements. So one thing that you can do, especially when we have this situation here where we made the parameter 1, is that wherever you have your pivot position, those are going to be the vectors that you choose for your basis. So that's one way to set that up. So we found a basis for W. Is this also a basis for M22? So that's a bit of a bigger question. So before we approach that, let's see, is there something in M22 that I can think of that is not represented by these? Yes. So here's an example. Let's say I've got, in fact, let's just keep this easy, and I'm going to go with 3, 0, 0, 0. If I have this vector, this is a vector that's in M22, but not W. I know it's not going to be in W because if I look over here, I need to have some of V in order to get this 3 in the top left. And then I'm going to need W. Well, actually, I want 0W because I don't want anything in those coordinates there. So really, the only vector I have to kind of play with to try and get this matrix is V. But if I take one of V to get a 3 in the top left, I'm going to get a 3 in the bottom right, and there's no way to get rid of it. So here's an example of something that is in my space M22, but which is not in W. So there's another way you can do this, right? You can say, suppose I have a matrix ABCD and try and write ABCD as a linear combination of these two vectors. And then you'll see that it fails. You can't define, like when we've done that in the past, we've tried to define like the alpha, beta, delta, gamma in terms of ABCD. And here you will find that you can't do that. Okay, so you'll get stuck trying to do that. So what this means for our purposes here, it is not a basis for M22. So we have to extend it to M22. So the good news is we already have one thing that we've got to extend, right? So we've got our V and W. So we have 3, 0, 0, 3. If I toss this vector in, now that's going to enable me to have not only matrices that have just one value in the top left, but also matrices that have a value in the bottom right alone. For example, if I wanted to get the matrix 0, 0, 0, 3, if I wanted that matrix, I could do that now by taking one of these minus one of these. So those would cancel out to give me the 0, but this would remain to give me that 3. So by tossing in this matrix, I've gotten not only matrices of the form with the top left, but also matrices of the form with the bottom right. We also have W, which is 0, -1, -1, 0. And this matrix is going to create a similar problem that this matrix did, where whatever the top left had to be, the bottom right also had to be. Here we have a situation where with whatever's in the top right also has to be in the bottom left. So I have to accommodate for that somehow, or count for that somehow, right? So I'm going to toss in another vector, and you could pick whether you want the non-zero entry to be in the top right or the bottom left. So I'm going to choose the bottom left for this one, and I'm just going to choose a 1, but it literally could be any number in this case. If you wanted this to be pi, have at it, right? So it doesn't really matter as long as that's the only non-zero entry. Because we're able to take any linear combination of these, that's why it doesn't matter. So for instance, if I wanted to get the matrix 3, 2, 0, 0, if I wanted to get this matrix, well, I'm not going to take any of this because I can get this 3 from here. So I'm going to write that as 3, 0, 0, 0. Now I'm going to need a 2 in the top right. So I'm going to need -2 of these to get that 2 in the top right. So we'll do -2. But that's also going to give me a +2 down here. So I'm going to subtract 2 of these to counteract that. And there we go. This way we'll be able to get this matrix 3, 2, 0, 0. Now, what I'm doing here is a lot less formal than what we just did in our previous example. In our previous example, we were like, okay, we've got our, what was it, x squared plus x, and then 1 minus x squared, whatever it was. So we've got those two. Let's try and write the standard basis elements in terms of those, and the one that we can't, then we're going to toss in. So we could also very well have done that here. So we could have said, okay, what's the standard basis for M22? And what do I need? Let me toss it in. So here's the deal. We haven't talked about the standard basis for M22 yet. So we will in a second, so we can see and we can kind of confirm these ideas. But in this case, sometimes you can kind of think about what pieces are missing or what problems your current vectors are going to give you to think about what you would need to kind of break free. So for example, what I noticed is that if I want something in the top left, the bottom right has to be the same thing. There's no way these can be different with the two matrices that I have. So that's what started me thinking about, what might I look for and stuff like that. So in this case, this would be one possible extended basis to M22. But in general, if I want to have the standard basis for M22, that's going to be where you have 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And this is going to operate a lot in the same way that the standard basis for Rn does, right? The idea behind the standard basis for Rn is that you have whatever your entry is in your column, you just pick up that many of the standard basis element, and that's how you create your vector. So same thing here, whatever matrix I have, like if I have the matrix 2, 4, 7, 5, I'm going to pick up 2 of these, 4 of these, 7 of these, and 5 of these. And that's how I'm going to end up getting this one here. So we could also have started out with these two vectors, tried to get, for example, this matrix from them, failed, and then thrown it in, right? So instead of 3, 0, 0, 0, I could have had just a 1 there. So this is an alternate way that you can think about trying to extend your basis. Think about what components are missing from your vector space. So just kind of a sidebar here, we've got the standard basis. This is going to be the case for whatever collection of matrices we have. It's going to be zeros everywhere except for one of the spots. So that means that the dimension of MMN in general is going to be M times N, because like I'm going to have M rows, each with N columns. So I need 1 for each of those spots. So here 2 times 2 is 4. So that's why we had 4 basis elements. Knowing the dimensions for these bigger vector spaces can be helpful because it'll help you know, okay, have I got the right number of vectors for my basis, or do I need to extend it? So I knew, knowing the standard basis for MN and its dimension, I knew 2 vectors was not nearly enough. In fact, I knew from the beginning the answer to this was no, because we only had 3. So there was no way we were going to get all of them, even if these 3 were independent. So it's helpful to be able to think about these kinds of problems in multiple different ways. So we're going to do one more example where we might see it's really a span, but it's given to us in a different way. So So I'm going to erase the board, write that problem on the board, and then we will work through it. Alrighty, so for example 25, we're going to consider this space. So this is, V is the set of all vectors that look like this. Its components are made up of U, V, and W, and U, V, and W are elements of R. And I wrote the questions over here so we could keep the definition of V here if it takes a lot of width. So we have to decide, is V a subspace of R3? Then we have to state its dimension. And then we have to say, is V equal to R3 and explain. So in this case, this is simply another way of writing a span of a set. And here's how. So this is actually kind of like when we were talking about the image of a matrix before, and we had like A times X, Y, Z. And then we wrote it as something kind of similar to this, just with X's, Y's, and Z's. So I'm going to rewrite this as just the U stuff, the V stuff, and then the W stuff. So the U stuff, we've got 1575. Ooh, sneaky, negative 30. U plus the V stuff, 7 minus 35 and 14. Plus the W stuff, that's the stuff left, negative 8, negative 40, and 16. Okay, so this is a linear combination because U, V, and W can be any real number. So these are any scalars. It's a linear combination of these three vectors. So V is equal to the span of these three, 15, 75, negative 30, 7, negative 35, 14, and negative 8, negative 40, and 16. So when you have a set presented to you in this manner, you can always write it as a linear combination of vectors. So you can write it as a span of vectors. And this is super helpful for A, because way back, what was it? It was on page 2 of my notes. Theorem 8, way back in theorem 8, that stated that spans of vectors are subspaces. So yes, by theorem 8. This is a span of vectors from R3, therefore it is a subspace of R3. So being able to change the format or recognize different formats is going to be really helpful. So next we have to state the dimension of V. Again, we don't want to assume that these three vectors form a basis. We now know that they span all of V, but are they linearly independent? How do we find out? Do you remember? Think about it while I'm erasing the board. So if they are linearly independent, that means that there's only the trivial solution to the homogeneous system, which means if I create a matrix out of them, it's got to go to, the only solution would be 0, 0, 0. Basically, right, I'm going to set each of these equal to 0 and then solve. So my U's I'm going to have first, 15, 75, negative 30, 7, negative 35, 14, negative 8, negative 40, and 16. And if you want to have the column of zeros here, you can. And like usual, we're going to do the row reduction, and also like usual, I've done that ahead of time so we don't have to spend a lot of time on this video going through that. So we're going to end up with the columns 1, 0, 0, 0, 1, 0, and negative 8/15, 0, 0, 0, 0, 0. So are we linearly independent or not? What does this matrix tell us? Well, it tells us that we have a row of zeros at the bottom and that we do not have a pivot position in the third column, which means we're going to have parametric solutions. So therefore, they are not linearly independent. So that means, because they're not linearly independent, that means that the dimension of V is not 3. The dimension of V is going to be less than 3. You can find the dimension of V without doing any more work, because I'll remind you earlier we saw that the pivot positions are going to be what forms our basis. So those first two columns, so from the U's and from the V's, that's where I can create my basis elements. So we're going to have 2 pivots, 2 basis elements, 2 for our dimension. So the dimension of V is 2. This is part B. That's it for part B. And actually part B makes part C really easy for us. So part C wants to know, well, is this space all of R3? And I can say immediately no. Do you remember why? So remember that the dimension of R3 is 3. So because the dimension of V is not 3, it can't be all of R3. It's missing some stuff. So no, the dimension of V is 2, and the dimension of R3 is 3. Those are not equal to each other. So therefore, they can't be the same space. So that's going to be it for this video. In our next video, we're going to dive a little bit deeper into the row space, column space, kernel, and image that we saw a couple of videos ago. In particular, when we talked about finding the row space, column space, kernel, and image, we just found them. We weren't worried about finding a basis for them, so we weren't worried about redundancies in our sets of vectors that define those spaces. Now we will be. So now we will want to find a basis for those elements or for those sets, and then use that to determine the dimension of the row space or the column space or the kernel and so on. So we're going to be taking these concepts and the concepts from a couple of videos ago and blending them together. So I'm looking forward to seeing you then. In the meantime, have a wonderful day. Bye, everyone.